get started? Or? People are good? We're good? Okay, great. Thank you. I had a nice talk with good people and had some good suggestions about some things we can, questions about what I talked about and some ideas, so it was very helpful for me. Thank you very much. I got my tea, ready to go. So again, we're going to be going until 2 o'clock, we'll have lunch. Hopefully everyone has some energy now to kind of go forward. And again, we're going to mix things up a little bit. I'm going to be showing you some other presentations as we go forward, talking a little bit more about the internals. But let's go back to the optimizer. I mentioned that. I mentioned that there is this path thing that the optimizer creates, and I was talking when we stopped about some of the problems that the optimizer had in the late 90s when I started with Postgres. But it's come obviously it's improved significantly since then. We have probably 2 or 3, 4 people who are very familiar with the optimizer, and we're always kind of making improvements to it. So the problem we originally had was that the system was generating too many paths, and it wasn't what we call pruning the path. When we prune a path, it's effectively, let's suppose that there are 1,000 possible ways to generate a query. Effectively, if we generate one that costs 10, and we generate another one that is higher than 10, we can just throw away everything that's higher than 10, because we already know that 10 is the lowest we've gotten so far. So the idea of pruning and eliminating possibilities as you're working through the optimizer is sort of a fundamental aspect. In fact, if you look at the optimizer source code, you'll see a file called prune.c, which is designed specifically to eliminate possible join paths, because the paths can generate, you can generate thousands or hundreds of thousands, tens of thousands of paths. They consume a lot of memory. They cause a lot of CPU because you have to keep comparing things. So there's this exponential type of growth in the optimizer, which is just endemic to optimizers. Every optimizer has this issue. And the more tables you have, the more possible paths you have. So if you think of 5 factorial, that's 120. 10 factorial is somebody big, whatever it is, right? I mean, I know 69 factorial is like 1 with 98 zeros after it, right? So 10 factorial is really big. 20 factorial is even bigger. So the idea that you're getting this exponential or factorial level type of growth is really bad. And the optimizer really tries to prune down what it does based on costs. And I'm going to show you some examples of that pruning that's going on. So let's take a look at this query. This is a very simple query. It's only returning 1 column, and it's joining 3 different tables. Okay? So 3 tables, you'd think that would be really easy. You can see here we're joining this to this and that to that. But in fact, this is the first stage of the optimizer. Now the way I got this output, there's a special compiler symbol called optimizer_debug. Optimizer_debug. And if you compile Postgres with optimizer_debug, you actually see this output when you run a query. I would love to actually enable this so you don't have to recompile, so you can just turn it on. Somebody during the break was telling me that in Oracle, there's a special way you can turn on and see all the paths that Oracle tries. And I'd like to have the same in Postgres without requiring a recompile. It would be a new variable, I guess you turn it on. But I haven't got enough interest in that, but I'm hoping to do it. But what we're going to do is we're going to walk through this particular output. And I apologize, it's not as large as I want, but I'll try and kind of talk about it as I go. So the first stage of running this query is to figure out how we're going to join we have 3 tables, right? So if we're going to join 3 tables together, the first thing we have to do is join 2 tables together, right? Kind of think about it, right? So if table 1 joins to table 2, and table 2 joins to table 3, I really have 2 options. I can join table 2 to table 3, or I can join table 1 to table 2. Those are my really only options. And again, you can start to see how the pruning works. I can't join table 1 to table 3 because there's no join here. There's no way of joining table 1 to table. You have to go through table 2. So this is a very simple example. Imagine 10 tables in a query. It's amazing the thing finishes at all. There's so many things, because if you have 10 tables, right, then it's like, well, I can join table 1 to table 2, and then table 2 to table 3, table 3 to table 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. But then I can also join table 1 to table 2, and then table 3 to table 4, and then join those 2 together, and then join table 5 to 6, and join that to table 1 to 4, and then take 7, 8, 9, 10, join those together, and join them. You see what I'm saying? As you get more tables, if you've ever run a query that took a long, like you had like 16 tables in it, and it took a long time, a lot of times that's just the optimizer trying to figure out, well, what do I do, right? How do I get you an answer as quick as possible? So you would never want to do this in an application. Like, thank goodness we can give the query to the optimizer and let it figure it out. Having been with the community so long, have you ever seen a query that just is like a full page of? We see those all the time, and I look at it and I can't even like find the from clause. It's just in there somewhere, but where some of our people can look at it and they're like, oh, this line 34, this right here, this is wrong. This is why you're through stuff. I don't know how they do it. I can't do it. But some people are really good at reading this incredibly complicated stuff here. But this is a very simple, right? 3 tables. So the first thing it's going to try is table 2 to table 3. And it's going to try, in this case, 3 different options. Remember, we talked about different join methods. So 3 ways it tries to join table 2 to table 3. The first one is a hash join. The second one is a nested loop with an index scan. And the third one is a nested loop with 2 index scans. Okay? So we've kind of pared down, it's tried a whole bunch of different options, and it says these are the 3 best ones. And the reason these are the best is because the merge join has the lowest cost, which like at 41 here. These are cost numbers. This is the startup cost. The first number is the startup cost, and the second number is the total cost. If you've ever run explain, you see these numbers, right? You see a number and then 2 dots and another number. How many people have seen that? Okay, a number, a dot, and 2 dots, another number. You're like, why are 2 numbers there, right? Like, have you ever thought of that? Like, what? And everyone says, oh, just look at the last number, but what does the first number mean? Do you remember I mentioned that when we do the joins, this has you have to do a lot of work to get this started. You have to create a hash. So that's what we call a high startup cost. Okay? So a hash has a non-zero startup cost. That's why it's 3. Okay? The nested loop has a 0 startup cost. That's good. Okay? But it's got a horrendously high total cost. Now the reason we have 2 costs here is there's some queries that use limit that don't necessarily need to run the whole query. I know this is like a mind bender. I know I have trouble understanding myself. And this whole process is something we kind of backed into. And let me back up and explain it. So normally you would think that if you're doing the optimizer, you would always want to pick the query that had the lowest cost, lowest total cost. That would make sense. However, if you're using a limit clause, everyone knows what a limit clause is, I think. Okay? So if you're using a limit clause, we're not going to run the whole query. If you say limit 1, we are not going to run all the rows and then give you one row. We're going to hopefully find out a way to give you one row without having to run the rest of the query. All right? So you kind of think when you add the word limit, and I'm going to show you some examples in a later presentation, when you add the word limit, you're telling the optimizer, I don't want all the rows, I just want the first row or the first 10 rows. Okay? So if you have a limit, it might be better to do a nested loop that has a huge total cost if you ran the whole query. But if you only want one row, not bad, right? I mean, think about how you'd run this if you told me you only wanted the last row, the first row, the minimum row. Well, okay, you just take the first row and you just compare it to every row and you're done. No, you don't have to hash the whole side, right? This is going to be hashing the whole table is going to be very expensive. So one of the reason we have two items here is because this one is cheaper total cost, but the second one has a cheaper startup cost. And that's going to be important. If there was a limit involved in this query, that would be important. Okay? Another aspect is this one. Why is this one here? Well, let's see. It's got an even higher cost than this one. So this one's 41. This one's 117, but it's got a 0 cost. This one is even higher, 2110. Why is it there? It has 0 cost, but it's higher than that one. Why would we have not pruned this third one? And the trick on this one is path keys. I mentioned path keys back up here with a little, right there. Okay. What's interesting about this one is it actually returns the results in order. It returns the results in order. This one does not return results in order. The second one does not return results in order. The third one does return results in order. Why is that important? I might need to do a merge join at a later stage. Remember, I'm joining tables 2 and 3. I might want to do a merge join with table 1 later. Okay? So even though the third one has a higher total cost, if I can do that and avoid a sort later for a merge join, that might be a win for me. So effectively, when the trimming happens, we end up keeping the one with the lowest total cost, the one with the lowest startup cost, and then any query that generates a unique path key. Because when I get to the next stage, I'm going to show you that ordering that I get by using an index in here might end up being valuable later. I know, it's like, it took us a long time to figure this out. About why that is important, because when we originally got the code, we had no clue why that wasn't getting pruned, and it took us a while. There were some other bugs that were preventing pruning, but this one was actually like pretty clear that they wanted that one kept, and you're like, well, why is that important? What does this thing do? It's trying to predict what potentially might be useful down the road. Second stage, remember I said I'm going to join table 2 to table 3. Now I'm going to try joining table 1 to table 2. That's my other option. Remember, I only have 2 choices, 1 to 2 or 2 to 3. Only choices. Now I'm going to join table 1 to table 2, and I end up with only 2 options here. One is a hash join, and one is a merge join. And not surprisingly, the hash join has the lowest total cost, and the merge join has the lowest startup cost. And in fact, you can see that down here. It says that there's a result. Cheapest startup path ends up being the hash join. Cheapest total path ends up being the, cheapest startup path ends up being the merge join, cheapest startup total path ends up being the hash join. Okay? And then putting that together, I get this, which is just a little smaller, but you can see it's now joining table 2 to 3, and then 3 to 1. Okay? And what you can see here is we've got one option here, which is a hash join of a hash join of 2 to 3 and then to 1. The second one, I have a hash join of 1 to 2 and then to 3. See the order's different here. 2, 3, 1, and then 1, 2, 3. Here's a hash join of a nested loop. So it's a hash join on the outside, but the 2 to 3 is a nested loop on the inside. With another sequential scan for there. And, now, so that was that. Then I have this one, a merge join with a nested loop and then 2 index scans. This is interesting. Do you remember I said that we kept one of the nested loops because it had a path key we might find useful later in a merge join? That's exactly what's happening here. Okay? You're doing a nested loop, you're using an index scan on the inner side. That makes sense, right? Because remember we decided if you do the index scan, if you can use an index over here, it's a lot faster, right? With a nested loop, right? But what's interesting is we're using an index scan on the outer side. And the reason we're doing that is so we can do a merge join without having to sort anymore, without having to do a separate sort step. Okay? And then we can use the existing index on table 1. So if somebody said, can you use an index to do a merge join? That's exactly what I'm showing you. Somebody asked this. Can you use an index instead of doing a sort? Can you use an index to do the merge join? That's exactly what you're seeing here. Okay? And then you get 2 results. You get what's called the cheapest startup path, which happens to be that merge join with the nested loop. And the cheapest total, it just ends up being the hash join. Databases love hash joins. I don't know if you've ever noticed that, but it's not only true in Postgres. Just hash joins just seems to be a very natural way for databases to do joins. Not good for small tables, not good for very large tables, but for middle-sized tables, which is what your joins are, you're going to see a lot of hash joins. Very, very popular. Any questions about that? I know it was pretty complicated, but I wanted you to kind of grasp what, you don't understand the whole thing, but the idea is just to grasp what is going on inside. That's what I was trying to show you, and again, illustrate it with some actual output from Optimizer Debug so you can see exactly what's going on. Yes, sir?
What are the dimension units of cost volumes and how are they calculated?
So the question is, what are the units of the cost? What are the units of cost volume? Right? And I would love to tell you that it was actually a number that made sense, but it's just a made-up number. The units of cost volume, technically, the retrieval of one sequentially scanned page, AK page, is a 1. So the base of the scan units is the cost of a sequential scan, of a single page sequential scan, and it's a 1. But we also have costs for sorting, we have costs for function calls, we have costs for random page access, we have costs for CPU calculations. If you look in the Postgres conf file, Postgres configuration file, you'll actually see these costs defined. So the numbers don't really mean anything except in comparison to other numbers. So it's kind of like we make up a unit, we assume sequential scan of a single AK page is 1. We then try and compute a CPU number based on that, and try and compute a random number based on that, and try and compute a function call overhead based on that. And it just kind of goes into this big slush of numbers. And we hope that when the query runs, it picks the number that's lowest when it computes all those numbers together. Okay? But I will tell you that those numbers are very estimated. They're very estimated. There's a lot of people who will look at the numbers in the config file and they're like, well, you know, is a random page that much more expensive than a sequential page, or how much does it cost to call a function? And so a lot of people who worry about the actual numbers in the config file and try and get those more accurate. In most cases, it doesn't matter. Like, let's look at this example. When we're pruning this particular example, I mean, the one number is 40, and the other number is, well, in this case, one number is 40, one number is 64. In this example, one number is 41, the other one's 178. Okay? So, again, those numbers are really not very close. They're pretty far apart. So in most cases, the cost numbers have to be super accurate. They just need to be kind of in the ballpark. And usually, if two numbers are very close, then technically, probably the execution times will be very close, and it doesn't really matter which one we choose. Now, there are some exceptions. For example, random page costs. If you're using SSD drives, solid-state drives, we'll recommend that you change random page cost. Instead of being 4 times more expensive than a sequential page, you maybe want to make it 1.1, because random and sequential on an SSD are very similar in performance characteristics. So you would probably want to modify that configuration parameter, and the optimizer will take that into account. You'll see it do more random I/O, more index lookups, because on an SSD, an index on an SSD is a lot quicker because you're not randomly waiting for the head to move and for the spindle to come around and all that other very expensive kind of work. So there are some legitimate reasons to kind of play with that. But again, usually they don't have to be super accurate. And the other thing about the optimizer that people forget is that, you know, if the optimizer takes 5 minutes to plan a query, and the query only takes like 5 seconds to run, something's wrong, right? I mean, you've spent 5 minutes trying to figure out how to run a query quicker than 5 seconds. So there is some sense that the optimizer doesn't have to be perfect, it just needs to be fast and get it close. Just get it close to where we want to be. Because there's a lot of variability in your system. It has to do with what table happens to be in the cache at that point, what table was most recently accessed. Some function calls are more expensive than others. Some random page access is more expensive than others. So there's a lot of variability, and trying to get these numbers exact really never works. But there are some major things like random page cost and some others that do make a significant example. And I can show you later that you can actually turn off, if you again look at the config file, you can turn off certain settings. So you could go in, you could start an SQL session, and you can change random page cost, and then run explain and see if your plan changed. Okay, so you try it with the defaults, and then you change the plan. And then you can also time it, and you can say, okay, if I turn off merge join, and it does a hash join instead, and I can time, and I can say, okay, before when it did a merge join, it took a certain number of seconds, and now when it's doing a hash join, now I can see is it faster or slower. And usually the community will get a complaint. We'll say it's doing an index scan, but if I turn off index scan and do a sequential scan, then it's faster. So something's wrong with the optimizer. And that's usually how we improve it, when somebody reports that it isn't doing what it should be doing, or it's chosen a plan that isn't the best one. And now that you understand kind of what all those numbers mean and what the different plans are, you can actually go back to your existing queries and start to turn off things, change the plans, run some timing tests and see what results you get. And you can determine maybe the optimizer didn't choose. It probably is correct 95% of the time, but there are a number of cases where it isn't. It's actually a very, very good optimizer because people complain to us, we look at it very quickly, we can send them a patch right away, or we can help them understand why it's making that mistake. And you do that enough, over and over again, over 19 years, and it gets pretty good. It's actually very hard for some of the commercial companies to fix things as quickly as we do. They email us directly. We can ask them questions right away. We can send them a patch. They can apply it. They can try it and see if it fixes it within 24 or 48 hours. None of the commercial vendors can do anything like that. So their improvements to the optimizer take a very long time, and that slows them down. Yeah. Thank you. Yes, sir.
Could optimizer learn in runtime and adjust in runtime?
Yeah, So the question is a very good one. Can the optimizer learn in runtime? And I will tell you there was a to-do item that I wrote and put on the to-do list exactly for that reason. Because the way it works now, the optimizer does not learn from the executor. Because the optimizer makes estimates on how many rows it's going to get, and how restrictive something's going to be, and how long something's going to take. But that information never gets passed back up to the optimizer. And I've always thought that the real way to go, the real way, the revolutionary way for the optimizer is to have some feedback coming back to the optimizer so that it will learn when it's made a mistake and will then adjust what it's doing. There is a risk to that because you can get like into a feedback loop where the optimizer starts to adjust itself like crazy. But I think I would love to see us move in that direction. I think the optimizer is probably very good. And I don't think it's going to get a whole lot better unless we go in that direction. Is that idea? The executor kind of knows what it's doing, and why aren't we telling the optimizer that? Even if we just, as a first step, even if we just said something in the server logs to say, we ran this query and this estimate would lay off, just something, some feedback for the administrator so they can know that things are not going well in this particular area. And right now we don't have that, and I would love, and that item has been on the to-do list for probably 7 years, and nobody's tried it. So I just really think there's a lot of value in at least trying it. Maybe it won't work, but I think it's really worth trying. I've never had the opportunity to do it, but I'd love to, yeah. And maybe somebody here will, because I think that's really where we have to go. To get to the next level of reliability and performance, I would love to see that. Yes, sir?
In Postgres, source code is some genetic optimizer.
Yeah. So the question is about the genetic optimizer. Let me see if I might have a slide about that. No, I don't. Okay. So, yeah, so there is something called a genetic optimizer. Where did I do with that? Oh. I don't think I have a slide about it. So the genetic optimizer, it sounds really fancy. The reason we have a genetic optimizer is because of that factorial problem. So remember I said if you do 3 tables, it's like pretty easy, right? It's like pretty simple, right? If you do 5 tables, okay, then you're, and then like 10 tables, I explained that was like, that was just terrible. Imagine like 20, 30 tables, right? There are so many ways of joining 30 tables that you're going to spend so much time analyzing that you're going to spend more time in the optimizer than you're ever going to save by generating a perfect plan. Imagine you you run it, you get a 30 table join, okay? Maybe it takes 30 seconds to run, okay? But to get that 30-second plan, it takes you 5 minutes. But I can get a 40-second plan in 10 seconds. I'm going to take that 10-second plan, right? Because if I can get a 40-second plan in 10 seconds, the whole query only takes 50 seconds. Okay? If it takes me 5 minutes to get a 30-second plan, which is 10 seconds quicker, it takes me 5 minutes and 30 seconds. Right? So it's not worth spending too much time in the optimizer to try and save a small amount of time in the executor. And that's effectively what the genetic query optimizer does. It uses sort of genetic pruning, or sort of what you think of as evolutionary pruning of the plans, and it just randomly picks some plans in a 30-table join, and then it does that across all 30 tables, and it comes up with sort of a good plan, not the best plan. It's never going to come up with the best plan, but a good plan, good enough so we can get it really fast and give you the answer real fast, right? So that's what it is. Technically, I think it starts when you join more than 11 tables. So anytime it's like 11 tables or more, it's going to use the genetic query optimizer. You can turn it off, but by default, it's going to automatically trigger at 11 tables. And it's going to basically say, I'm no longer going to try and find the best plan. I'm just going to try and find a good plan. And I'm going to do that by just not trying every possibility, but just randomly trying a sufficient number so I can get a sufficiently good plan to get you your answer. And that's a traditional problem with large joins, is that if you don't do that, the optimizer will just run a very long time. Yeah. Yes, sir. Yes.
If this random, sort of deterministic random, so if you make the same explain statement a number of times, will you get the same plan?
So the question is the genetic query optimizer deterministic? Meaning if you run it again, will you get the same number? There actually is a random seed that you can set in the config file, which will force it to use the same randomization every time you run that query. If you don't set that random seed, then technically you will get a different plan every time you run that query. And that way, I mean, you're right. If you don't change that seed, then every time you run that query, you're going to get a different plan. It's usually going to be pretty good, but it's not going to be perfect each time, right? Because just the way the optimizer works. Yeah. But there is a way of kind of controlling that seed. If you wanted, particularly for testing, right, you would want to run the same query over and over with the exact same plan. You would just reset the seed every time before you run the query and you get the same plan. Yes, sir.
The question is slightly related to the real-time feedback. So right now the optimizer it's controlled by the PostgreSQL form settings. So is it at all possible, like in the future or anything like that, or do you plan to make it adjustable, on a, for example, session level? So I know that a query, all my queries behave well, but one single query is not very well, and I know how to fix it with those settings, but I will mess up all my other. And probably the real-time feedback would fix it too. It would see what's going wrong, but for the time being, is it
right?
doable?
Of course, yeah. So if you look at the Postgres comp file, you will see a section for the optimizer, and it will say enable sequential scan, enable index scan, enable, and you can turn those off within a single session. In fact, I would tell you probably never turn them off within the comp file. Like, there'd be really no reason to imagine running your server and turning off like sequential scan or index scan. Like, that would be horrific, because either now all of a sudden every query would use an index scan, or every query would use a sequential scan. That would be just terrible. But again, almost every setting in the config file, unless it says restart, it can usually be set within a session, or even within a transaction, and then reset to whatever you want it to be. So that's very common, that you just begin a transaction and then set local your variables and then run your query and then just commit it. And then all the variables will go back. Once you're done, you didn't even reset them. Set local, if you do that inside the transaction block, it'll just set local and then you just set your settings, and then when you commit the transaction, everything resets to what it was before. And that's a very common way of, because you would always only change them within a little block of, yeah. And if you're testing, obviously the same process would be. Other questions? Yes, sir.
How optimizer choose the index for index scan?
So the question is, how does the optimizer choose an index for an index scan? So effectively, the way it works, every table potentially can be sequentially scanned, right? Because that's just you don't need an index to do a sequential scan, right? The data is there, just do a sequential scan. And then every index is also considered for an index scan if there is, actually every index is going to be considered for an index scan, because every index gives me a unique path key, right? So effectively, I think the way it works is if the path keys elements are mentioned anywhere in the query, we will consider that index. So for example, if you created 3 indexes on column A, B, C, we potentially could have sequential scan and then 3 index scans, potentially possible. I think we have some code in there, so if only tables A and C are mentioned in the query and not B, we won't consider the scan on index B, because there's no sense in carrying it around, because we're not going to use it. But I don't know actually how smart we are about trimming off those indexes. So, I mean, one of the takeaways from that is that indexes are not zero cost. When you create an index, every time you do an insert, you're going to have to add to that index, right? We're going to have to clean up those indexes entries on delete, and a lot of updates may require the index to be updated. So they're not a zero cost option. Sort of creating an index for every column on your table is not probably a good idea. But in addition to that, you have the issue of the optimizer is going to have to consider each index every time you access that table to determine. So there's cost even there. But effectively, that's what this path key is. It didn't know back here. It did not know whether this was useful or not. But I think it did because it saw that column in the index was mentioned in one of the joins. So I think we only pick up indexes that are also either have a constant comparison or have the column mentioned in one of the join clauses. But when you start to read the code, the actual source code, this gets really complicated. You're starting to look at, we could probably pull up the block that actually spins through all the indexes on the table and determines whether each of the indexes is a valid one to consider as a path. And you basically run through it, and that's how you create your indexes. Yeah. Yes, sir.
Let's pretend that the human is smarter than computers.
Yeah.
And I know what query plan needs controls and can I use Postgres that query plan?
So the question is, suppose that humans are smarter than computers. So the question is, can you tell Postgres how to execute a query? So one thing you can do that I mentioned, the gentleman in blue there, is that you can turn off certain things. So if you wanted a hash join, you could turn off nested loop and merge join, and that would force a hash join to happen. Similarly, you could turn off index scan or sequential scan. But the problem in this particular example is there's no way to turn it off per node. There's no way to say, I want this table to be index scanned, but this table to be sequential scanned, and I want a merge join on this part and a hash join on that part. That is what Postgres can't do. We've been talking about sort of adding it But our goal obviously is for the optimizer to figure this out. So if you're needing to change, it means we've made a mistake and we'd like to fix it. I know there are some commercial versions of Postgres where you can put hints in. I mean, I work for Enterprise DB. They make a version where you can use Oracle hints inside of the query, like Oracle, right? But again, the community doesn't like that. We would rather have the optimizer work 100% of the time, which may be unrealistic. The danger we've always had with administrators, obviously I'm not going to do that by talking anymore. Well, how did I get here? Oh, here we go. Sorry. The danger with hard coding, the danger with hard coding in the actual optimizer output is that if your data layout changes, your hard coding doesn't change. So obviously, it's a maintenance problem that you have to keep maintaining that plan, and then you need to know when to change it because people's data does change a lot. So if you think of large organizations, usually like fixing a plan is like good for short term. Like you need to get it working now, and then you'll come back later and figure out how to get it working right. So I think for short term it makes a lot of sense. Long term, obviously, we want the optimizer to work, and we want the optimizer to be able to change as your query, as your data changes, because usually people's data isn't static. It's a very common question. Yes?
Does Postgres cache query plans?
Does Postgres cache query plans? Yes, it does. If you use prepared statements, it caches them. If you do not use prepared statements, it will not cache them, meaning it will reevaluate every time.
And what strategy per connection?
Right now, it's only going to cache it per connection. We have a to-do item, which would create what we call a global prepared cache, so that one session could prepare the statement, and another session could make use of that prepared plan. Right now, we do not have the ability to do that, but it has been on the to-do list for quite a while. And I know Enterprise DB's looked at doing it, and other community guys have looked at it. It's something I think would be very nice to have. Yeah, I agree. We should have a global cache. We don't. Yes, sir.
Can optimizer use parameters to choose the plan?
So can the optimizer use parameters to choose the plan? Indeed, it can. The optimizer will, by default, use statistics that are defined for the table and auto-updated with auto-vacuum to determine whether constants mentioned in the query are significant for whether constants used in the query actually restrict enough so we can use an index scan. It actually very closely controls what plan is chosen based on what statistics are available for certain constants that appear in the query. Yeah.
But if it's not a constant but a parameter, like
so it's not like prepared statements, right? So prepared statements, I was going to go into this. It's actually really interesting. The way prepared statements work, this is going to kind of surprise you, is that when you prepare a statement, you don't really give it constants, right? You just placeholders. So the way that the code works is that the first 5 times that you run the query, we will use the constants that you give us, and we will re-plan the query every single time. The parsing we only do once. Parsing is done when you prepare it. But the first 5 times we will re-optimize that query with the constants you give us 5 times. If during those 5 times we determine that the constants you give us generate a plan that's very similar to a plan we would choose without constants, like a generic plan, then from 6 onward, for the next, I think, 100 runs or 200 runs, we will use a generic plan that is not affected by the constants you supply us. And then I think after 200 runs, we'll do it over again. We'll replan for 5 times. Make sure your new constants are also not changing the way we would normally generically plan this without constants. And then we'll go forward for another 200. So it's actually kind of a learning thing. It doesn't automatically use the constants the first time. It'll run it 5 times. And if those 5 runs are supplying constants which are very similar to the generic version, we will use the generic version for X after that, and then restart again.
And if given constants affect query plans,
so if the given constants do affect the query plans after 5, then we will re-optimize for every constant. Yeah. So the goal there was that we knew that if we started using generic plans that do not rely on the constants, we could generate some really terrible plans. So we figured if we've gotten 5 runs through and all those constants are pretty predictable, then we can go forward and know that we probably have a good. And then, but we're still going to retry after a couple hundred plans, a couple hundred executions, and then redo that process to make sure nothing's changed. And we did that probably 4 years ago, and nobody's ever had us a question about it. Like a production question. We've never had anybody say, well, I used prepared plans and then all of a sudden it went berserk and my machine melted down. No, for some reason that seems to have worked really well. But we were very worried about how those prepared plans were going to potentially impact the way this. I don't know of any other system that does what we do, but I think it's a good solution. It's worked very well in practice, so we haven't had any complaints about it. It's a very, obviously, good question. Other questions? Yes, sir.
How optimizer understand how many rows can return set returning function?
Okay, so how does the optimizer understand how many rows are going to be returned by set return
For example,
function?
if I nest array and join.
Yeah, very hard to explain. We do allow you to do an alter function and tell us how many rows are going to be returned. So you can actually tell when you can actually either when you're defining the function or after, you can actually say this function on average is going to return X rows, and you can also say how costly the function is. So if you're doing, very expensive calculations that take a long time in a function, you can set that cost as part of the function, or use the alter function and change the cost of the function. That's about the best we can do. Again, until we have the feedback from the executor, which this gentleman's going to write here. He's squirming in his seat, right? Until we have that feedback, then yeah, you have to tell us how costly the function is, and on average how many rows that function is going to return. And if you don't, I think we assume like, I don't know, 10 rows or something very arbitrary. It's not disappointing, but that's, yeah. The whole costing of functions is really a bad, just an area that doesn't work very well, frankly. Just because it's like a black box to us. We don't really know. What we do know actually is if you create an expression index, all of a sudden we have huge amounts of information about that function. So we know, not so much for set returning functions, but in terms of the distribution of the output of a function. If you create an expression index, we create statistics on the output of the function. And if you call the function in a where clause, we have a very good estimate of how many rows are returning. Yeah. So it's kind of surprising that it's kind of a way we get around the problem. Other questions? Yes, sir.
How do we convert early plans?
So I'm sorry, the question, we convert early plans?
Yes, it's then you decide do you want the cheapest setup or cheapest total cost with order binding something.
Okay, so the question is, if we have two results, cheapest startup and cheapest total, how do we figure out which one to use, right? So, I haven't really gone into this, but effectively the limit clause is not, how to explain this? The limit clause is not really part of the optimizer, okay? So the optimizer is going to pick the cheapest startup and the cheapest total, right? But there's a later stage that's going to look and it's going to say, okay, this query would take a long time to run, it's got a very high cost, but they only want one row, and therefore they only want like 0.012% of the output, and we just take the limit number and we multiply it by the cost, and we basically say, if I only run like 0.2% of this query, what will the total cost be? And we look at the startup cost, we're like, well, that's obvious, even though it has a 0. Even though the other one has a cheaper total cost, it's obvious that if I run 0.002% of this query, even if the cost is very high, I'm going to get the answer very quickly. So that's a stage that happens after this, where we kind of apply the limit part to the query, which is not kind of in the optimizer itself. It's kind of a separate stage that we do. Yeah, I don't have a slide for that, unfortunately. I have a slide about limit later, but it doesn't show you the internals of it. Other questions? Yes, sir.
Are there some default plans for 20 tables or 30 tables, cache or nested, or what is it used as default?
So are there some default rules for when the various join methods are used? Okay, there are actually no default rules. And the reason for that is because we really want this to be dynamic. I mean, obviously, if we could write the optimizer with some defaults, it would be real easy, right? But the problem is that different tables have different widths. So, like, some tables have like just 2 columns of integers, right? That's very easy to fit in memory. Some tables are very long. Some tables, have very different distributions for common values, and some of them are all random, all unique. So there really are no defaults at all. It's really all based around that costing parameter because, for example, if I say, and I'm going to show you an example later, but if I say like, column equal 3, that's probably going to use a nested loop. But if I say column greater than 3, right, then I'm probably going to use a merge join because all of a sudden I've changed the number of comparisons like dramatically. So there's really nothing hard-coded in there, and that's by design. Because we always want to use the costing because there's just so many things going on in the optimizer. I mean, there's some very simple databases where, like, it'll join based on the order of the from clause tables. Like, that's horrific, right? Just, like, I've seen, in the old days, back in the 90s, there were some databases where if you said table 1, comma, table 2, you would get a different join than if you said table 2, comma, table 1. Your actual order of your tables matter in the optimizer. Postgres does not do that. Everything is cost-based. So there's nothing hard-coded in there at all. Yeah?
When genetic algorithm decides that it's good enough to stop, is the time limit or something?
So that's a great question. I never really thought about it. So is the genetic query optimizer, like, how does it know when to stop? Like, when is it? And in fact, if you look at the genetic query, if you look in the Postgres config file, you will see a separate section just for the genetic query optimizer. So there's the actual costing parameters for the genetic query optimizer are actually in the config file. And what I think the logic is we'll try like, I think we try like 5% of the plans. I think that's how it works. So there's no real time limit, but instead of trying everything, we'll just say we're going to try, maybe 10 versions for each table or something like that. And then we're just going to stop after that. So there's no, what you're getting at, is there any kind of feedback loop that says, oh, I've gotten closer, I'm going to kind of stop? I don't think it works that way. I think it basically just kind of says, I'm going to try X versions, and then I'm going to stop, and then I'm going to try the next table and do that many versions. And then it just kind of brings up a result. There's no, I don't think you can put a time limit on it to tell it when to stop. I don't think, does anybody know, I don't think there's any like feedback loop that says, oh, my plans are getting very good, because there's really no definition of good. It's really hard to like know what good is. So I don't know that code completely well, but based on the config parameter, I think it's just a random kind of tempting thing. Other questions? Oh yes, Pam.
Okay. You talked about selectors. What about how other this was for propagate queries used such as queries or update queries and other?
Yeah, that's a great question. So the question is, we talked about select queries. What about a complex update or a complex insert, right? And kind of rolling back here a little bit, effectively all of the select, insert, update, delete, and some utility commands, everything that goes through that optimizer executor is really this. It's kind of awkward. It's really all the same query to us. Aside from insert, which is kind of a special case, you know, and a delete is really a select with a delete, right? So instead of like a select is select and return the rows, a delete is select and delete the rows, right? An update is select and update the rows, right? Insert's a little awkward because that's like kind of, you've got constants there, but if you do an insert select, right? Think of insert select, that's a select with an insert, right? So all of those commands get planned virtually the same. They all go through the optimizer, they all have where clauses, they all potentially have joins. You can do, in Postgres, you can do joins in the from clause. For delete, you can do joins in an update. So we treat them exactly the same. They get optimized exactly the same. The execute is slightly different because we do something after we select it instead of returning to the user. That's really the only part that's different. So it's the same process going through here, yeah. That was a little surprise to me, like, wow, it's just the same. Because when you look at the code, you know, you're looking at the code and you're thinking, is this a select? And you're like, well, maybe it is, but maybe it isn't, because it's all the action at the end that controls what happens, yeah. Other questions, yeah?
I could elaborate on the executor in case of delete or insert. If I, you know, form a really large delete, which is very obvious, but will the executor be smart enough, you know, to delete a row? It will select, gets something, and then deletes, or it gets everything and then deletes again.
Right. So the question is, when you're doing a big delete, do you really select all the rows and then delete them, or does it happen? And it happens the way you would hope it happens. So, I mean, I'm making it very simplistic. So when I said select everything, delete it, if you look at the code, what happens in the executor is you've got this this sort of tuple source, row source, and when you generate the row, if it's a row that's to be returned to the user, we call the libpq to sort of shoot it back to the client. If it's not a select, then we just call another thing that just deletes that row, and then it gets the next tuple source and then runs it straight through. So it isn't technically doing a select and delete. It's doing per row, and instead of shooting that row back to the user, it's then deleting it, or it's updating it, or inserting it if it's insert select kind of case. Yeah. Other questions?
What about query transformation? Is any query transformation phase?
Yes. Is there a query transformation phase? Yes, I didn't go through that. The query transformation phase is up here. The rewriter is the query transformation phase. That's what handles views. and rules.
Yeah.
And it's sort of like a macro processor, which basically kind of understand the query. And when you do a select on a view, it's the rewriter that inserts the view text into the query. It modifies the from clause, it modifies the where clause. If necessary, it modifies the target list. So effectively, when you're doing a query that mentions a view, it's taking the view and like merging the view text, the view query, into your query before it gets to the optimizer.
Yeah.
Okay? And that's important because obviously there's all sorts of optimizations that can happen when that view is expanded, and that's how we want to make sure that we get all optimization by doing it.
Rewrite query, for example, exist and not in, and some other ways.
Okay, so that's a good question. So do we have anything that would convert an exists to an in query or an into a not exist? I believe there is some code which will try and, yeah, I'm showing my age. There was a time when those were separate, they were completely different. But I think we've gotten better at kind of pulling things out of subqueries. In fact, there's some cases where when you do an in, it'll take the subquery and it'll put it in the from clause, so that the in like is gone. Because depending on how your query, there are some optimizations, but that's happening not necessarily in the rewriter. That's happening in the optimizer when it kind of figures out, okay, I can move this. We call them pull-ups, and we also push stuff down. So we can push restrictions from the query down into the subquery, and we can also push subqueries up. But I don't know the actual rules of when we do that. But we do that in certain cases when we can, when we're sure we can.
For example, if we have select 10, 12 tables, but we sure that 7 of them are not useful. Yeah.
Yeah, we
join
can
and then
yes, we can throw those away, particularly if there's a primary key and we know that it's a one-to-one join. Then we know that effectively doesn't do anything for us, so we can throw it. The query, for example, you mentioned it, you join to a table, but the table is not, none of the table's columns are returned in the target list.
Yeah, and
right.
I have a foreign key.
Right, and you have a foreign key, so you know it's one, yeah. Those type of things we can just throw away. And because people don't write those things, but utilities write those things all the time, right? And that what we call pruning out. In fact, if you look at the release notes, you'll see some like mentions of sort of table pruning, and it's kind of cryptic because very few people understand what it is we're doing. So I don't really go into a lot of detail in the release notes. But we do that, and we do mention it. Try and mention the release notes to say that we've improved table pruning, and people are like, well, "What's that?" And that's exactly what it is. When we can prove that a table doesn't do anything, we can just throw it away. And I think we've only recently done that optimization, so maybe I think it's 9.4 or 9.3 we added that. So it didn't exist before, but it was something people were asking for because a lot of utilities create these references to tables that have no purpose, and we realized that was. And I want to say 9.4. I want to say that's pretty new. That's pretty new. Yes, sir.
Why Postgres won't optimize common table expressions?
Why won't Postgres optimize common table expressions? We had a thread, we had a discussion about that, I want to say 5 months ago. And I think it should be optimizing common table expressions. And I think we're getting close to maybe implementing that, hopefully in 9.5. I'd like to see that. Right now, when you write a common table expression, that common table expression cannot be moved into it has to be executed first. You can't move stuff around. The reason it was originally written that way is somebody felt that the standard, the SQL standard, required us to do that. And we've looked at it now, and we don't think that's true anymore. So we think maybe that was incorrect. So we now are going to give people the ability to do that. It might be a variable, or it might be a flag. We're not sure how we're going to do that. But I've been disappointed that we don't optimize or move it, and I think we're losing performance by not doing that. Yeah, there are some advantages to what we do, but I think there's probably more disadvantages. Yeah, I do. But yeah, we definitely discussed it 4 or 5 months ago, and I still have the email in my mailbox saying, "Hey, let's do something on this," because I think it's a problem. Yeah. Yes, red team.
Do you know why limits on deletes and updates?
Do I know why limits on deletes and updates are not supported? Well, the problem with limit is that unless there's an order by, the limit is really useless. So we really have, I mean, unless you want to delete random rows, right? Right, yeah, so we'd have to add order by to update and delete. And then we could, and then people would look at this kind of funny. They'd say, "Why is there an order by clause on your delete?" And like, well, there's this update thing, and that's where it really, so I have not, you're the first person to ask about it. I think it would be kind of neat. The way we tell people to do it now, you ready for this? The way people do it now is related to the previous question. Common table expression, okay? Delete returning. I'm sorry, select, return, right? And then the common table expression then deletes the rows that come out of the above with the limit. That would be the way I would tell people to do it now. Yeah. Now whether we want to add that to delete or update, I'm not sure. I think we probably might ask people like, is common table expression good enough for you? And maybe that is enough. Because when we start to add delete, yes, Alexander, I'm sure you have a good answer.
If you do this using common table expression in committed isolation level, then if some rows was deleted between it was selected and actually delete statement, they wouldn't be deleted. You can delete less rows than you have a limit in the select. So this is kind of difference.
But
select for update.
But do we get a new snapshot within a common table expression? Don't we use the same snapshot for?
You know, if the row was updated, then you get new inside the yes, but yes, select for update.
Yeah, I guess you have to do select for update. Yeah, that would make sense.
Order by in update can be useful feature separately because you can get rid of the rows if all your updates updating table in the same order. Because now you can easily get that log just in two updates, which updates the same.
I see what you're saying. Yeah. I see what you're saying. I not thought of that. Yeah, that's interesting. So by controlling the update of column order of rows, you can prevent. That's interesting. Yeah, this is the first I've ever heard of this idea. So I have to think about it for a while. This sounds good.
I wrote about this for probably 3 years ago, but then something everybody said.
Why am I not surprised? Yes. Other questions? Those are some really good questions. Yes, sir.
Is there any plan of having maybe somewhere in the future a low-level API for simple queries which can skip entirely all the parsing of SQL section, all the optimizing query planning by manually maybe providing the entire query plan?
Right, so the question is there thought of doing some kind of low-level API that will allow you to do stuff quicker by avoiding a lot of this?
Yeah.
Probably the current way you would do it is with prepared statements. So obviously with a prepared statement you're avoiding the parsing, and after the 5th time you're avoiding the planning. So that probably is, I would assume that would be enough. Obviously copy command does not do any parsing. So the copy command is a raw insert into, and in fact, Heikki made some improvements in the past couple of years to allow, for example, the way we update indexes with copy is in a batch mode instead of doing one by one. So I would be interested to know what you want to do that isn't already supported now, like what it is you want to, what you're hoping to win by doing that. So I don't know the answer, actually.
Maybe I'm mad enough to manually construct the exact query plan.
Yeah, but already prepare is going to do that for you, so I'm not sure. It seems like it would be a lot of work for you to pass us a query plan. That would be pretty monstrous. And the problem is, even if you did, it would probably break the next time you did something, right? Because the code's changing. So yeah, I would be interested to know what you want to do differently than we can't do already. That would be my question.
Well, maybe something like the handler socket library for MySQL does.
Yeah, I know MySQL has like sort of that low-level stuff.
Yeah.
Yeah, I'd be interested to know what Postgres would gain by doing that. I'm not sure the answer. It might. I don't know. Other questions? Yes.
Yeah, just want to comment on that. We actually have what we call fast path API for function calls specifically, and it's kind of deprecated and not recommended to use because it's not any faster than prepare state. So that kind of proves the point that it's probably not worth it. Right. That's the thing. If we're going to, if you're going to win 2% or 1%, then we're going to be like, we don't. As an SQL database, we really just don't go there. Something it's a really awkward API that gets a single-digit kind of win. Probably not worth it for making this code more complex and the API more complex. So the question is, what would be a significant win versus what we have? And I'm not sure what the answer would be there. And yeah, Heikki's saying that we had a couple hacks in there to do that, and they're not really any faster either. So yeah, you'd have to do some research and give us some numbers on exactly what you're trying to do and why it's going to be faster than what we have. Yeah, that would be your hurdle, basically. Other questions? Okay. So again, we kind of talked about, so this, let me just finish, let's go through the optimizer. So effectively, once we've gone through all this optimization stuff, we get to something called a plan. And a plan is basically what gets sent to the executor. So that's like the instructions. It's much more detailed than a path. A path is just a sort of a way of getting at the data. A plan is like a recipe. Okay? It's a program that we pass to the executor. The executor runs our program of how to get at the data. So the executor is very dumb. It doesn't have a lot of smarts in it. It just takes a plan and it just runs through the instructions that we give it. The instructions may say index scan. The instructions may say merge join. The instructions may say sequential scan. Whatever it says, it's going to run, call this function, do this aggregate. It's going to just run those instructions. And the instructions are coming in something called a plan, which effectively just has a whole bunch of information about what you should do. And it's, let's see here, so yeah, it's just basically going to run this little program. And this is what the plan output looks like. Again, very similar to the other stages. It looks like JSON, but it's not. Key value pair, nested, and so forth. Okay, and it's just running through. And then here's our output. So all through that executor, all through the planner, the parser. This is the output we get. It just happens to be one row that we get out. If you think I'm lying about what's going on, there is a way of seeing the various stages of the parser, so of the query. So if you take a look again at the Postgres comp file, you'll see a config variable called log stats executor, log stats parser, log stats planner, log stats rewriter.
And it will then, once you turn that on, again you can turn it on for a single session, it will give you the time it took for each of the stages. So you can actually look inside and say, oh wow, my parsing took this amount of time. Oh, then my optimizing, my planning took this amount of time. So here's the stats on the parser. Here's the stats on what we call parse analysis, which is after the parser. Here's the stats on the rewriter, the planner, and the executor, and then you can see exactly how long each of the stages took here. And you can see how much I/O they did, and how much memory's not listed, but how many, let's see, context switches you had. So you can kind of see what's happening while each stage is going on. And if you're curious, like, okay, my query took 5 minutes, well, how much time was parsing, how much time was planning? You can get that information by turning on the various stage reports. You probably wouldn't want to turn it on for everybody, but maybe for a single query, turn it on and you get this out. Okay. I have a whole bunch of slides here about internals, but I'm not going to really go over it because really in question of time, there was one presentation I wanted to show you in addition. So let me just kind of fly through here. Again, these are some slides about the internal structure of Postgres, the header for the tuples, the index layout, the various ways that we do multi-version concurrency control. If you're interested in that, again, I have a multi-version concurrency control presentation on my website. There is a video of that, a couple videos, so if you want to sit down and be bored for 45 minutes, you can do that. It is a very complicated presentation. You'll see slides like this and slides like this. Let's go over to number 0, please. The slide number 0. There's one more presentation I wanted to kind of show you to finish it out. And our gentleman back there is going to get us a different presentation because I wanted to just show you the optimizing one more time. Great. So, this is another presentation actually called Explaining the Postgres Query Optimizer. And what's amazing is all this is going to make a lot of sense to you now because these slides now make sense. The idea of sequential scan, and index scan, and bitmap scan. The idea of sort of doing a constant and getting different outputs. So here is an example. I actually create analyze statistics, and when I select a very common value, I get a sequential scan. I like that. When I select a medium value, I get a bitmap index scan. And then when I select a rare value, I get an index scan. Okay? But even more than that, this kind of example, I think, is really illustrative. What it's showing you is when I use different constants, this is what we talked about with the prepared statements. When I send different constants to the query, to the system with the same query, just different constants, what you can see is that I'm actually getting a sequential scan for the very common values in red. I'm getting a bitmap heap scan for the medium values, and I'm getting an index scan for the very rare values in pink. And this is all the optimizer. I haven't told the system which one to use. The system automatically knows based on the constants and based on the statistics. The system automatically knows which one it needs to pick. Okay, this is going through that whole process that I just explained of trying to figure it out. In the same way, when I do a join, the join changes based on what I've given in the where clause. Here I'm saying equals 33, it does a nested loop, right? You've seen that slide before. If I say greater than 33, I get a hash join. Again, the optimizer is doing its work. It's saying, oh, I'm going to return a lot of rows now. I can't do a nested loop anymore. I want a hash join. If I get rid of the where clause completely, I get a merge join. Because it now thinks there's going to be a lot of rows being returned, and it's automatically falling back to a merge join, and you can see there's no indexes, so it's doing a sort. Remember we talked about earlier, if the indexes exist, it'll try and use them. If the indexes don't exist, it'll do a sort on its own. Okay? Same thing here. If I, well, anyway, the order of the tables doesn't matter. Now, if I add some statistics, all of a sudden, what used to be a merge join becomes a hash join. So now the optimizer is using these statistics to get better estimates, and therefore it's chosen the hash join. If I add some indexes, remember we talked about indexes improving what the optimizer can do, and exactly that happens. Now when I do a query, what used to be an nested loop is still happening, but now it's using 2 indexes instead of doing the separate sorts for me. Okay? So that makes it kind of easier. I don't have to sort. I can use the index and do my nested loop that way. It even knows about strings, not only constants but strings. If I use an AAA, which doesn't exist in the table, it does a nested loop, but as soon as I do XXX, which all values are XXX, it actually does a hash join, so it knows, hey, I'm now doing a very common thing, I have to fall back to a hash join. And finally, limit. We talked about limit, controlling what happens. Remember that startup cost thing, where we talked about startup cost? Here, when we do a query with no limit, we get a hash join. But as soon as we add a limit 1, it falls back to a nested loop. Because remember, nested loop has a very low startup cost. Right? And if I do a limit 10, it still does a nested loop. Because it still thinks it's cheaper. But if I do a limit 100, then it's like, all right, now we're getting too high of a total cost. I'm going to now fall back. And it actually falls back to a hash join. Okay? So, what have we done? We basically talked about how the query is executed, how it goes across the network, how it arrives on the other side, how it gets tokenized or scanned, how it gets parsed, how it creates a query structure. We talked about the optimizer, how it does certain costings, how it generates a whole bunch of paths, figures out which one the quickest one is in terms of the quickest startup, the quickest total. Then we talked about the executor a little bit, and then finally I've kind of shown you and walked through the executor with this presentation, which is also on the website, which also has recordings of me talking for 45 minutes about the slides, which effectively goes through the various ways that the query optimizer automatically adjusts to what you're doing. So, again, I've enjoyed this session because I don't get a chance to talk a whole lot about the internals. Normally everyone's like, how do I do X? Right? When are we going to get feature Y? Right? That's usually the type of things that I'm talking about. But this stuff excites me because it's just really amazing what it does. There's so much going on there, not only in Postgres, but pretty much all the relational databases. They're doing some really, really amazing stuff and making application programmers' job a lot easier by not requiring application programmers to do nested loop joins and hash joins and merge joins inside their application. They're giving it to the database. The database is doing its job, returning the results as quickly as possible. And I think that's really the big strength for relational systems, is that understanding what all of it does. You send this abstract, declarative statement, hey, give me these rows with these restrictions, and you figure out how to get it for me. And just unburdening application programmers from that detail, I think, is really the huge win for relational systems. Not only Postgres, but pretty much all the systems. And I think Postgres does it very well, and uniquely Postgres allows you to watch what it does very well. You can see what Postgres does because you can see the source code. So, thank you very much. I know I'm out of time, but I think we had some really, really good questions. I'm glad we were able to take the questions as we go, because that way you're able to kind of get, some information, and we can kind of talk about details of things I'm talking about at the time. So I appreciate that. Again, I'll be here till Wednesday, so I'll be here for the rest of the week, and be glad to talk to you. And I want to thank you for presenting. And obviously Magnus is up after lunch, and I'm looking forward to his presentation as well. So thanks very much.